Welcome to this problem explanation. In today's session, we'll tackle LeetCode problem number 902, numbers at most n given digit set. This is an exciting problem where we explore how to count numbers that can be formed using a specific set of digits. Grab your notes, and let's dive in. Here, we are tasked with solving a problem involving a set of digits and a target number. The input includes an array of strings called digits, where each string represents a single digit from 1 to 9. Importantly, these digits are sorted and distinct. Additionally, we are given an integer n, and our goal is to determine how many positive integers can be formed using the digits in digits such that these integers are less than or equal to n. The problem allows us to use each digit in the digits array as many times as we want when forming numbers. The output will be a single integer representing this count. To summarize, we are essentially counting how many valid numbers can be constructed under these constraints. Now, to understand the problem better, let's review the first example. Suppose the input is digits equals 1, 3, 5, 7, and n equals 100. The numbers we can form using these digits, while staying under or equal to 100, are 1, 3, 5, 7, 11, 13, 15, 17, 31, 33, 35, 37, 51, 53, 55, 57, 71, 73, 75, and 77. In total, there are 20 such numbers. Therefore, the output for this example is 20. This demonstrates how we can repeatedly use the digits to form numbers of different lengths while ensuring they don't exceed the value of n. Let's look at another example. Here, the input is digits equals 1, 4, 9, and n equals 10000000000. This time, the target number is significantly larger, which means we have many more possibilities. Using the digits 1, 4, and 9, we can form all numbers less than 10 to the power of 9, and the total count of such numbers is 29,523. This example highlights how the size of n and the number of digits in the digits array can drastically affect the number of valid numbers we can construct. Next, consider the case where digits equals 7 and n equals 8. Here, the only number we can form using the single digit 7 is 7 itself, which is less than or equal to 8. Since no other numbers are possible, the output is 1. This example illustrates how the problem behaves when we have very limited options, either due to a small digits array or a very small value of n. Finally, let's discuss some edge cases to think about. For the smallest inputs, we could have a single-digit digits array and the smallest possible n, such as digits equals 1 and n equals 1. For the largest inputs, we might have the maximum possible n, which is 10 to the power of 9, along with the largest digits array containing all digits from 1 to 9. Another edge case occurs when n is smaller than the smallest number in digits, such as digits equals 5 and n equals 4, where no valid numbers can be formed. Finally, there's the case where n is an exact match for a number we can form, like digits equals 1, 3, and n equals 31, where the number 31 is included in the count. These cases help ensure our solution is robust and handles all scenarios effectively. To solve this problem, we need to determine how many positive integers can be formed using the provided digits array such that they are less than or equal to a given number n. One approach to consider is the brute force method, where we generate all possible numbers using the digits in the digits array, for lengths ranging from 1 to the number of digits in n. After generating these combinations, we filter out the numbers that exceed n and then count the remaining valid numbers. While this method might seem straightforward, its computational complexity is a significant drawback. With d elements in the digits array and k digits in n, the worst-case scenario involves d to the power of k combinations, making this approach impractical for larger inputs. The brute force method is therefore not suitable for efficiently solving the problem, especially when n or digits is large. A more efficient approach involves mathematical counting combined with digit-by-digit analysis. Instead of generating all possible numbers, we use combinatorics to directly count the valid numbers. The key insight here is that numbers formed with the digits array can either have fewer digits than n or the same number of digits as n. For numbers with fewer digits, the total count is straightforward. For a number with L digits, we can quickly compute the combinations as digits (L). For numbers with the same number of digits as n, we need to carefully analyze each digit. Starting from the most significant digit, we ensure that the prefix of the number remains valid. If a digit in digits matches the current digit of n, we continue to the next digit. If not, we stop further exploration. This approach is significantly more efficient, with a complexity of O log n asterisk digits, making it well suited for larger inputs. However, it does require careful handling of cases where digits or n has special constraints. Another approach to consider is using dynamic programming, specifically a technique known as digit DP. This method involves defining a state, such as dp, POS, tight, where POS represents the current digit position, and tight determines whether the numbers being formed are constrained by the digits of n. The transitions between states depend on whether we use digits that are smaller than the current digit of n or match it exactly. By summing up all the valid states, we can compute the total count of numbers that satisfy the given conditions. While this method can be very powerful and extendable to more complex variants of the problem, it requires a deep understanding of dynamic programming concepts and can be intricate to implement. The complexity is typically O log n asterisk digits, but the added complexity in implementation may not always be necessary for this specific problem. For this problem, the optimized approach using mathematical counting and digit-by-digit analysis was chosen. This strategy strikes an ideal balance between simplicity and efficiency. It avoids the computational overhead of brute force while being more straightforward to implement than the dynamic programming approach. By leveraging combinatorics and carefully analyzing the digits of n, we can efficiently count valid numbers without explicitly generating them. This method is particularly well suited for handling large inputs, with a complexity of O log n asterisk digits. While it does require special handling for edge cases, such as when digits has limited variety, these challenges are manageable compared to the intricacies of implementing digit DP. Overall, this approach is the most practical choice for solving the problem, offering clarity, scalability, and alignment with the problem's constraints. This problem challenges us to determine how many integers can be formed using a given set of digits such that the numbers are less than or equal to a target number, n. The digit set is provided as strings, and the first step involves parsing these inputs. Specifically, we extract the digits from the input array and convert the target number n into its string representation, n_str. This conversion allows us to access each digit individually and also determine the length of n, which we call len_n. For example, if n is 345, then n_str becomes 345, and len_n is 3. With this setup, the problem can be broken down into two main parts. First, we count numbers with lengths smaller than len_n, as these automatically satisfy the condition of being less than n. Second, we handle numbers with lengths equal to len_n, where additional constraints come into play. For the latter, we must analyze each digit of n to ensure the numbers formed are valid and adhere to the restrictions imposed by n_str. To solve the problem, we first count numbers with lengths smaller than len_n. For every length from 1 to len_n1, the total number of numbers that can be formed is calculated as k(l), where k is the size of the digits array, and l is the current length. This formula works because each position in the number can be filled independently with any digit from the set. Once these counts are calculated, we add them to a running total. Next, we focus on numbers with lengths equal to len_n. Here, a more detailed approach is required since each digit of the number must be checked against the corresponding digit of n_str. For each digit in n_str, we identify valid digits from the digit set that are smaller, equal, or larger. If a smaller digit is selected, we can freely fill the remaining positions with any digits, as these numbers are automatically less than n. If the current digit is equal to the corresponding digit in n_str, we proceed to the next digit and continue checking recursively. However, if a larger digit is encountered at any position, no valid numbers can be formed beyond this point, and we exit the loop. These steps ensure that all constraints are respected while calculating the total count. Additionally, edge cases must be considered, such as when the digits array is empty or when n is too small to form any valid numbers. By carefully handling these scenarios, we avoid errors and ensure accurate results. The key insights for solving this problem involve breaking it down into manageable parts and leveraging efficient techniques. First, analyzing the problem digit by digit allows us to handle constraints incrementally, reducing overall complexity. By separating the counts for numbers with lengths smaller than len_n from those equal to len_n, we simplify the logic and make the solution more structured. Another important optimization is pre-computing powers of the size of the digits array. For example, calculating k⁻l ahead of time lets us quickly determine the count of numbers for lengths smaller than len_n, saving computational effort during the main calculation. Additionally, the recursive approach to handle constraints for numbers of length len_n ensures that we account for all valid combinations while adhering to the rules imposed by n_str. To support these calculations, we rely on specific data structures. Converting n to n_str simplifies digit-level comparisons, while the sorted digits array allows us to efficiently identify smaller, equal, and larger digits during recursive processing. Optional memoization can also be used to store intermediate results of recursive calls, especially when overlapping subproblems arise, further reducing redundant computations and improving performance. Now, let's analyze the complexity of the solution. The time complexity is k*len_n, where k is the size of the digits array and len_n is the length of n_str. This accounts for the recursive digit-by-digit processing, as we iterate over the digits array for each digit in n_str. The space complexity is len_n, which comes from the recursion stack. To illustrate, consider the example where digits is 1, 3, 5, and n is 345. First, we convert n to n_str as 345 and determine len_n is 3. We start by counting numbers with lengths smaller than 3. For length 1, there are 3*1 equals 3 numbers, 1, 3, and 5. For length 2, there are 3*2 equals 9 numbers, such as 11, 13, up to 55. Next, we count numbers with length 3 by analyzing each digit of n_str. For the first digit, 3, we consider smaller digits like 1, equal digits like 3, and stop processing for larger digits. We repeat this for the second digit, 4, and the third digit, 5, applying the same logic. Summing all these counts gives the total number of valid numbers that can be formed. This step-by-step approach ensures that we honor all constraints while keeping the computations efficient. This implementation solves LeetCode problem number 902, numbers at most n given digit set. The goal is to determine how many numbers can be formed using a given set of digits such that the numbers are less than or equal to a given n. ###explanation. The function at most n given digit set takes two inputs, digits, a list of strings representing the allowed digits, and n, the maximum number. 1. Convert n to a string. Since we need to compare digits of n individually, converting n to a string, n_str, is helpful. We also calculate the length of n, n_len, and the number of digits in the given set, digits_len. 2. Step 1. Count numbers with shorter lengths. For numbers shorter than n, all combinations of the digits are valid. For each length L from 1 to n_len1, there are digits_len valid numbers. We accumulate this count in the variable result. 3. Step 2. Count numbers with the same length as n. We iterate through each digit position of n. For each digit of n, compare it to the available digits in the set. If a digit from the set is smaller than the current digit of n, all combinations of the remaining positions are valid, so we add digits_len, n_len I1, to result. If a digit from the set matches the current digit of n, we continue checking the next position. If no digit matches, we stop since no further valid numbers can be formed. For final adjustment, if all the digits of n are matched, we include n itself as a valid number by adding 1 to result. This approach ensures that all possible numbers are counted efficiently without generating them explicitly. The time complexity is proportional to the length of n and the size of the digit set, making it highly efficient for large inputs. Here, we're implementing the solution to determine how many numbers less than or equal to n can be formed using the given digit set. First, we convert the number n into a string so that we can work with its digits more easily. We also determine the length of n and the size of the digit set. Now, the first step is to count all numbers that can be formed with lengths smaller than the length of n. For example, if n has 3 digits, we calculate the total possible numbers with 1 and 2 digits using the formula digits len raised to the power of the length. This gives us a baseline count. Next, we focus on numbers that have the same length as n. To do this, we iterate through each digit of n, comparing it with the digits in the given set. For each digit in n, if a digit in our set is smaller, we add all possible combinations of numbers that can be formed with the remaining positions. If we find a digit in the set that matches the current digit of n, we mark it as a candidate to proceed further. If no matching digit is found for the current position, we know that it's impossible to form a valid number, so the current result is returned immediately. Otherwise, the loop continues to check subsequent digits of n to account for all numbers that are valid. Once the loop completes, we add 1 to the result to include the number n itself, as it's a valid number if all its digits can be formed using the given set. Finally, the total count of numbers that meet the criteria is returned. This implementation ensures we efficiently calculate the result by leveraging the properties of digit sets and powers of their lengths. To solve this problem, we begin by initializing some key variables. First, we convert the given number n into a string, which allows us to analyze its digits individually. Here, n is 100, so n_str becomes 100. Next, we determine the length of n as n_len equals 3 and the length of the digit set, which is also 3. We initialize result to 0 to start accumulating our count. Now, we start by counting all the numbers that are shorter in length than n. For numbers of length 1, there are 3 possible combinations using our digits, 1, 3, and 5. This gives us 3⁻1 equals 3. Similarly, for numbers of length 2, there are 3⁻2 equals 9 combinations, such as 11, 13, 15, and so on up to 55. Adding these together, the total so far becomes result equals 3 plus 9 equals 12. Finally, we move on to numbers that have the same length as n, so we begin analyzing the digits of n_str, which are 1, 0, and 0. Starting with the first digit of n_str, which is 1, we compare it to each digit in our digit set. Since 1 matches the first digit in the set, we mark that a match is found by setting has_same_digit to true and stop looping further for this digit. Next, we move to the second digit of n_str, which is 0. Here, we compare 0 with the digits in our set. Since 0 is smaller than the smallest digit in the set, which is 1, there are no valid matches. At this point, we set has_same_digit to false and terminate the process. We return the current value of result, which is 12. Therefore, the final output for this example is 12. In this example, the digit set is 7 and n is 8. We start by converting n into a string, so n_str becomes 8. The length of n is 1, and the digit set also contains only one digit, so digits_len equals 1. We initialize result to 0. Next, we count numbers shorter than n. Since n itself is only one digit long, there are no numbers shorter than this length, leaving result unchanged at 0. Now, we proceed to count numbers of the same length as n. The only digit in n_str is 8, so we compare it with the single digit in our set, which is 7. Since 8 is greater than 7, no match is possible. We set has_same_digit to false and return the current value of result. Therefore, the final output in this case is 0. Here, we analyze a new example where the digit set is 1, 4, 9, and n is 50. We start by converting n into a string, so n_str becomes 50. The length of n is 2, and the digit set contains 3 digits, so digits_len equals 3. We initialize result to 0. To begin, we count numbers shorter than n. For numbers of length 1, we can form 3 valid numbers, 1, 4, and 9. This gives us 3⁻1 equals 3, which we add to result, making it 3 so far. Next, we turn to numbers of the same length as n, and start analyzing the digits of n_str, which are 5 and 0. We begin with the first digit of n_str, which is 5. Comparing it with each digit in the set, we see that 5 is greater than 1, so we add all combinations that can be formed using 1 in this position and any valid second digit. This adds 3⁻210 equals 3 to result, bringing it to 6. Similarly, 5 is also greater than 4, so we add another 3 caret 210 equals 3 to result, making it 9. However, since 5 is less than the next digit in the set, 9, we stop adding at this point. As there's no exact match for 5, we set has underscore same underscore digit to false. At this stage, we terminate our process and return the current value of result, which is 9. Therefore, the final output for this example is 9. To analyze the time complexity of our algorithm, let's break it into two main steps. The first step involves counting numbers that have lengths less than the length of the target number, n. For each possible length, from 1 to n underscore len 1, we calculate the total number of numbers that can be formed using the given digit set. If the digit set contains digits underscore len digits, the total combinations for a number of length L are digits underscore len caret L. By summing these combinations across all lengths, the total work involved in this step is represented as O, digits underscore len caret 1 plus digits underscore len caret 2 plus digits underscore len caret n underscore len 1. Since the highest power of digits underscore len dominates the growth rate, this step simplifies to O, digits underscore len caret n underscore len 1. This captures the computational effort of counting numbers with lengths shorter than n. The second step focuses on counting numbers that have the same length as the target number, n. For each position in n, we iterate through all digits in the provided digit set. If a digit in the set is smaller than the corresponding digit in n, we calculate the total combinations of numbers that can be formed for the remaining positions. This is computed as digits underscore len caret n underscore len I1. If the digit matches the current digit of n, we continue to the next position. If no matching digit is found, we terminate early. In the worst case, we compare every digit in the digit set with every digit in n, leading to a time complexity of O, digits underscore len asterisk n underscore len. Adding the complexities from both steps, the overall time complexity of the algorithm is O, digits underscore len caret n underscore len 1, plus digits underscore len asterisk n underscore len. The dominant term depends on the relative sizes of digits underscore len and n underscore len. Now let's discuss the space complexity of the algorithm. The space usage is minimal beyond the input and output. Specifically, the digits array has a size of digits underscore len, and the target number n is converted to a string, requiring O, n underscore len, space. Additionally, a few integer variables, like result and n underscore len, are used for intermediate calculations. Importantly, no extra data structures are created during the computation. Therefore, the overall space complexity of the algorithm is O, n underscore len, making it very efficient in terms of memory usage. To better understand the advantages of this optimized approach, let's compare it to a brute force solution. A naive method would involve generating every number from 1 to n and checking whether each number can be formed using the given digit set. Generating all numbers in the range would require O, n, time, and for each number, verifying its digits would take O, k asterisk log, n, where k is the number of digits in each number. Combining these, the total time complexity of the brute force approach is O, n asterisk k asterisk log, n, which is highly inefficient for large n. In contrast, the optimized solution leverages combinatorics to avoid explicitly generating all numbers, drastically reducing the computational cost. This makes the optimized approach significantly faster, especially when n is large. Finally, let's consider the best, average, and worst-case scenarios for the algorithm. The best case occurs when the digit set contains only one digit, minimizing the number of combinations that need to be calculated. The worst case happens when the digit set includes all possible digits, such as 0, 1, 9, and the target number n is large, leading to the maximum number of combinations and comparisons. In this scenario, the time complexity reaches O, digits underscore len caret n underscore len 1, plus digits underscore len asterisk n underscore len. The average case falls somewhere in between, depending on the size of the digit set and the structure of n. Across all scenarios, the optimized solution is a clear improvement over brute force approaches in terms of both speed and memory efficiency. When solving this problem, there are several common pitfalls to watch out for. First, it's easy to misunderstand the problem scope and assume that the digits in the given array must appear in the same order as in the number n. This is not true. Digits can be used in any order as long as they form valid numbers, so your logic should take this into account. Another frequent mistake is mishandling leading zeros. For instance, constructing a number like 012 using digits 0, 1, 2 is invalid, as numbers cannot have leading zeros. Always ensure your solution skips these cases. Additionally, overcomplicating your recursive logic can lead to inefficiencies. Some approaches try to generate all possible numbers recursively, but this often results in exponential runtimes. Instead, leveraging combinatorial techniques can streamline the process significantly. Lastly, edge cases are often overlooked. For example, if n has fewer digits than the smallest number you can construct with the given digits, this can cause off-by-one errors or incorrect results. Testing edge cases such as n being a single digit or the digits array containing only one element is critical for a robust solution. Another mistake to avoid is ignoring the base conversion patterns inherent in this problem. It's helpful to recognize that this challenge is similar to counting in a custom base defined by the digits array. Missing this insight often leads to unnecessarily complex or inefficient solutions. From an interview perspective, the key insight here is to approach the problem as a combination of combinatorics and digit-by-digit comparison. Breaking the problem into smaller steps, such as counting numbers with fewer digits and then handling numbers with the same number of digits as n, can simplify the solution. Interviewers often expect you to avoid brute force approaches that generate all possible numbers, so focus on leveraging patterns like pre-computing valid digits for each position to improve efficiency. Additionally, always demonstrate awareness of edge cases during interviews. Be prepared to discuss scenarios such as when n is very small, when the digits array includes 0, or when all provided digits are larger than the digits in n. Explaining your approach clearly, especially how you handle fewer digits, equal digits, and the constraints of the digits array, is essential to stand out. This problem also shares similarities with other problems on LeetCode, which can provide valuable practice and insights. For instance, LeetCode 139, Word Break, uses a dynamic programming approach to build valid combinations, which is conceptually similar. LeetCode 357, Count Numbers with Unique Digits, involves combinatorics and digit constraints, making it another closely related problem. LeetCode 233, Number of Digit 1, focuses on counting specific digits within a range of numbers, which overlaps with some techniques used here. Finally, LeetCode 788, Rotated Digits, requires careful digit analysis under constraints, much like this problem. Now, in terms of alternative approaches, dynamic programming can be a powerful method to solve this problem by counting valid numbers while naturally handling constraints. The advantage of this approach is that it maps well to problems with digit-by-digit constraints, but it does require more memory and can be trickier to implement. Alternatively, combinatorial counting can be used to directly calculate numbers with fewer digits and then handle numbers with the same number of digits as n through precise digit comparison. This approach is often more elegant and efficient but demands careful attention to off-by-one errors and edge cases. Another approach to consider is backtracking, which involves generating all possible valid numbers and counting those that fall within the bounds. While this method is intuitive and works well for smaller inputs, it becomes inefficient for larger inputs due to exponential growth and possibilities. Lastly, there's the custom base conversion approach, which treats the problem as counting in a base defined by the given digits. This approach is highly efficient for analyzing patterns and constraints, but it requires careful implementation to ensure accuracy. Both of these methods have their pros and cons, so choosing the right one depends on the input size and complexity of the constraints. By understanding these various approaches and their trade-offs, you'll be well equipped to tackle not only this problem but also similar ones in the future. Thank you for watching. We reviewed the solution, discussed its key takeaways, and highlighted the importance of combinatorics in solving problems like this. Be sure to practice similar problems, and stay tuned for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!